So yeah, so I'll tell about this project that I'm doing with Harry. It's been like a month and a half since we started it, and it's quite a lot of fun. And it started one day when Harry came into my office and he brought me this game, which is called Dobble, like this. And it's very simple. So it has a bunch of cards. Oops, can you see the cards? And all you have to do is just find two symbols that are the same on both cards.
Clover.
Can anybody? Huh? Clover, yes, very good. Let's take another pair of cards. Whoops.
No, man.
Yes, very good. So you see, it's quite exciting. It's not so easy to find these symbols, but it's also not clear how to make this game. So if you look at this card, so what it has is 8 symbols, and of course they are kind of rotated and so on. But they're basically on each card there are 8 symbols, and if you count how many cards there are, then in a set there are 55 cards. And so this begs the obvious question, how do you make these cards? Because they have to have the property that for every 2 cards, there has to be exactly 1 symbol in common. So you could say, you know, given the number of symbols on each card, how many cards can you make with this property? Okay. And well, if you think about it, and Harry, so his son introduced him to this game, and he was thinking about how would you make this game? And the kind of well, intuitive idea is maybe it has to do something with lines, because if you draw lines on a plane, then usually they have the property that they have exactly 1 point in common. So for every pair. Of course, there's an exception. If the lines are parallel, then they don't have a point in common. But still, this idea of using the lines to make the game is a good one. And so let me explain how you can mathematically describe what's going on and how you can make this game of any size, well, of arbitrarily large size. And so the mathematics behind this is called projective plane. Okay, so what is a projective plane? So basically, this idea with lines, we need to overcome these 2 problems, that the lines, we need them always to intersect, even if they are parallel. And we also want to discretize the structure, because the plane, there's like infinitely many lines. We want to somehow discretize it. So let's look at the case, the projective plane of order 2. So let's put some axes, x and y. And so if it's order 2, we start by making a grid, a 2 by 2 grid of points. And we assign to these points the usual coordinates. So this will be the origin, this will be 1, 0, this will be 0, 1, and this will be 1, 1. And now we can draw some lines. And so what we're going to do is we're just going to draw basically all possible lines through these points at all possible slopes. So we're going to draw a horizontal line, another horizontal line here. But now imagine it's like when you have railroads, even though they're parallel, it looks like at the horizon they meet. Okay? So these lines, they will meet sort of at horizon, at infinity, and we will put also a coordinate for this point as well. So we're going to say that the x coordinate is infinite, and the second coordinate, we'll just put the slope of this line. So these are horizontal, so the slope is 0. So we can also draw vertical lines like this. Now they also meet at the point of infinity. So this we'll call, so it has x coordinate 0, but the y coordinate we're going to call infinite. Actually, sorry, what I'm going to do is I'm going to call this infinite. So it's like you walk infinitely far at the slope infinite. So basically the second coordinate for these points with the first coordinate infinity, the second coordinate will be the slope. So here it's 0, here the slope is infinity. And finally, you can also walk at 45 degrees, sort of angle like this. But then, just like here, there were 2 lines, so there has to be another line parallel to this one. And you can obtain it by shifting it up by 1, so it would start here and kind of go like this. But so we're going to be working modulo 2, because this is projective plane of order 2. So going up like this is slope plus 1. It's the same as slope minus 1. So we're actually going to go like this. So these 2 lines are parallel in this world. and they meet at the point at infinity. So we're going to draw something like this. Okay, so this is slope point at infinity, slope 1. And then to complete the picture, we're going to add another line that goes through all these points at infinity. So this will be the line at infinity. Okay. So you get this kind of picture. And you can, I draw it for the order 2, but you can just do for larger orders as well. So here, if you can see, is a picture of order 3. So we just start instead with the 3 by 3 grid. And again, we have 3 lines horizontally. Oops, it's in mirror. 3 lines vertically, 3 lines at slope. Oh gosh, it's so hard to point. Okay, so 3 lines at slope +1 and 3 lines at slope -1. And then also the vertical lines with infinity. And then there's the line at infinity as well. Okay, so the same idea. And you can do this for larger orders too. So the higher the order, the more there will be different possible slopes, and the more there will be points at infinity. So for example, next order would look something like this. So it just gets more spiky. All right, so now
so you don't do slopes like 2/3 or something.
Yeah, so you want these lines to go through the points basically. So basically you should think of the slope as follows. You always make one step horizontally, and then how many steps you make vertically. If you make one step horizontally and 0 steps vertically, the slope is 0. If you make one step horizontally, one step vertically, the slope is 1. And then finally you have this kind of infinite slope where you go only vertically. All right,
but you can't go 3 steps to the right and then 1 up.
Well, so 3 steps to the right. So that's going to be the same probably as going on. Yeah. So okay. So let's look at this. I mean, eventually you will end up. So if you look at this, you have some lines that do that. Like for example, it's really okay. So for example, the orange line, it goes through these 2 points. So you can sort of, well, I don't know. I mean, yeah. Anyway, I mean, everything is sort of modulo some numbers. So you will get various possible slopes, but because you're working modulo, then some of them might actually be the same. Okay. All right, so let me describe let me just make a list of all the points that we have in the general case, and also what are the lines. So okay, so let's write down the points. So the points are as follows. So we have a grid. So here the grid was very small. It was just this 2 by 2 grid of these points. But in general, we'll have a grid of, let's say, so I will assume now that the size of this grid or the order of the plane is a prime p. Okay, so there will be these points here. And so x and y, there will be from a finite field of size p. And there will be p squared of such points. So this will be the grid. Then there will be these points at infinity when you walk at different possible slopes. So these I will label in general by the point of infinity at slope A for every possible slope. And so there will be p points like this. And then finally, there will be this another point here that has infinite slope and it's infinitely far, where all the vertical lines meet. So I'll call this point infinity, infinity. And there's just one point like this. Okay? So now in total, the number of points is going to be p squared plus p plus 1. And yeah, so these are all the points. Okay, so now let's write down the lines. So we'll label them also by, so we'll think of the lines as basically sets of points. So we have these p squared plus p plus 1 points. That's a set, and the lines are just subsets of that set. Like here, these are subsets of size 3. And in general, I will label these lines by 2 parameters. And so that this parameter will be sort of slope. Oops, this is too small, probably. Bigger. So this is slope, and this you can think of it as kind of a shift. And okay, so let's just write down this first line. So these will be all points of the form x and ax plus b, some linear equation. So x is in a finite field. And we will also add the point at infinity at slope a. So union the point at infinity at slope A. Okay. So this is just a generalization of this idea, what I was doing here, and you can do it for any prime. And so this is naturally the slope of the line, and this is how much you kind of shift it vertically. So we have these lines, and so these will be sort of all possible lines with all possible slopes that are finite. Then we will have the lines with infinite slope. So these are the vertical lines, like here. So how do they look like? They will be of the form d y. So where y is again in the finite field. And then we attach a point at infinity, which is going to be this vertical, infinitely high point, which I call infinity infinity. So that's the point all the way up here. And so these are just lines at that go vertically, and they start at x coordinate b. Okay. So these are the vertical lines, and then finally there will be the special line at infinity, which I call it's the set of points I call S infinity infinity, and this will be basically all the points at infinity of all possible slopes. Okay, so F is an infinite field, and plus the union of this point at infinity, the vertical point at infinity. All right, so now what you can see is that, well, how many of these lines do we have? Well, we have, so all possible A's and B's, we have P square lines that are with the sort of finite slopes, and we have P lines with infinite slopes, and then we have one line that is at infinity, and you can see the total number of lines is P squared plus P plus 1. Okay. And so let me now summarize these various observations. So what we have, so in general, so if we define, let me just define a general projective plane. So you can see here. So basically, what we're going to have is so it will have order d. So what that means is that what we need is d squared plus d plus 1 points and lines. And the second property, what we want is that there will be d plus 1 points on each line. And also the same number of lines through each point. Okay, so basically, in general, for a projective plane of order d, what we want is d squared plus d plus 1 points and also the same number of lines. And there should be d plus 1 points on each line. And through each point, there should be d plus 1 line. So for example, here, so we have indeed, so here this d is 2. So we have 7 points and 7 lines. And we have 3 points on each line, including this circle. And we have also, for every point, there are 3 lines that go through. Okay. So this is, yeah, maybe, okay, if there's some questions, maybe you can just unmute yourselves.
Oh,
okay.
yeah.
You also want?
Marius, I wanted to ask a question.
Yeah.
Do you also want points of the form a comma infinity?
Yeah, no. So, yeah, so basically, the first coordinate infinity will mean that it is at infinity. And the second coordinate will mean that it what is the slope, and there's the possibility that the slope is infinite, but we will not have sort of we will not have the other way around.
Yeah. Okay.
Yeah, and also, you know, then if you would do the other way around, then you would end up with a bit more. You have like d plus 1 squared points, and it will not be exactly. Okay, so now, so let me point out a couple of things. So first of all, so basically what I described here by this construction. You can check that obviously we have the right number of points and lines, and you can also see obviously each line has exactly p plus 1 points, And so this is a bit harder to check, but you can also check that for every point appears in exactly p + 1 lines. And in fact, if you wanted to check that statement, you would have to sort of, you'd have to look at two lines and find where those lines intersect. And for finding this intersection, you have to solve some simple equation, and you would have to divide at some point. And for this division, you need a field, basically. And so that's why this construction works whenever there's a finite field. So in particular, it works for any, so when the order of the plane is a prime, or also for a prime power. All right, so, okay, so now, yeah, so but there's all kinds of other nice things about these planes. For example, yeah, so for example, any two points determine a unique line, which is something that we're used to. If you have 2 points, you can call it a unique line. Similarly, also any two lines determine a unique point. This is the point where they intersect. In fact, so here it seems like I gave this point some, special coordinates, so it looks like this point is special, but in fact, all the points are the same. So there's a notion of symmetry, like an automorphisms. Basically, you can relabel the points and relabel the lines. You can send actually any point to any point. You can send any line to any line. So even though this line is kind of like a circle, in fact, it's equivalent to any other straight line. And in fact, you can send any 2 points to any 2 points and so on. All right, so let me state a couple of things. So now we know that they exist for prime power orders, but do we also know what about the other orders? And so there is a result about the other orders, which is called Reiser Chrovla theorem. And so what it says is that it does not exist. This projective plane does not exist if D is congruent to 1 or 2 modulo 4, but not a sum of 2 squares. Okay, so this rules out several cases. So let me just make a list. So let's say we start with 2, 3, 4, 5, 6, 7, 8, 9, 10. Keep going, 11, 12, 13, 14. All right, so now, so what does this theorem do? It rules out the order 6. So 6 is congruent to 2 modulo 4, but you cannot write it as a sum of 2 squares. Let's see. So it rules out 6, and it rules, in fact, out infinitely many cases. It rules out also 14. Now, there are some cases that are harder to rule out. So, for example, 10 also can be ruled out, but here you need a huge computer search. And the case 12, for example, is still open. So even though it's a very small, seemingly small case, it's hard to iterate through all possible subsets of these points, and so it's hard to exhaustively check that it doesn't exist. All right, so this is basically what we know about projective planes.
Wait, Maris, can you give some intuition why these cases cannot occur? Because with your definition, like if you did this D is the number P on the top board, right? The prime that you want to have for your projective plane.
Yeah, so it's not obvious. Like if you want to show this, I think you look at some matrix that describes this, and you look at its eigenvalues and do some math. Yeah, it's not obvious that this should be the case. In fact, I didn't know this result, and it's kind of surprising that you can rule this out actually.
But are the definitions on the top board going to be inconsistent, or is there something else to a projective plane that?
Oh yeah, no. So I mean, so the definition is this, and so what was this was a construction when the D is a prime power when there's a finite field. But so but the definition is just this.
Thanks.
Okay. So right.
Mars,
Yeah?
don't you also need that every 2 lines intersect at a point?
I may have, I think that just this was fine, but in case you need more, you can look it up on Wikipedia. But I think it's just this.
No, I think the axioms require that every two lines intersect, or you need to say something about a line that is not, a point that is not on the line.
Yeah, so, okay, so there might be more things that, so basically you should just think of whatever this construction gives, you know, it has all kinds of nice properties, you know, that's the thing we're interested in. And it has some formal definition with various properties, and maybe I didn't list all of them. And in fact, there are some kind of degenerate cases that you know, maybe you want to rule out and so on. But yeah, sorry if it was unclear. But yeah, so basically for the purpose of this talk, what we're interested in are basically objects that you construct like this. And you know, they're sort of like, they live in a wider world that you know, have a more general definition. All right, so now let me move on. And so what I'm going to do is now actually, so yeah, and you know, this projective plane basically describes the possible games you can make. You know, it tells you how many cards you need, how many figures there will be on each card, and so on. All right, so now, of course, what we want to do is we want to make this quantum. And we will have a little bit of a problem to do that. So let me just draw a picture to kind of say where we're heading. So let me make a big matrix. That's going to be the incidence matrix of this projective plane. And so let me say that the lines are here and the points are here. And there is a 1 somewhere inside if the corresponding point lies on the corresponding line. And because these lines and points can be grouped in such a natural way in these groups, so we will also split this matrix in the following way. So there will be p squared, p and 1 here. There will be also p squared, p and 1 points here. And what we will kind of focus is on a subset of this incidence matrix. And so what does this subset correspond to? It corresponds to throwing away one line, and the line we're going to throw away will be the line at infinity. So we're just going to discard this line here. And we're going to discard also all the points that lie on this line. We're going to discard these points. And so, okay, so what does this mean? So in this incidence matrix, actually, this line at infinity has these points at infinity. So it has ones like here. And so that means that these are, if we remove this line at infinity, we're removing all these points. Okay? And so we're going to just focus only on this part. And what this part describes is something that also has a name. It describes what's called an affine plane. So this is just basically a D by D grid, or in our case, a P by P grid that has all possible lines, all possible slopes, but it doesn't have these points. So for example, if P equals 2, then this affine plane is just going to look like this. And this is also what you get if you throw away this line of infinity. And then, well, you can draw it how it looks like for bigger sizes, for example, for P equals 3, it looks like this. It has some, okay, it has also these diagonal lines, and it has these curly lines like this. Oops. So it has only the P by P grid, and then has all possible lines with all possible slopes. Horizontal lines, vertical lines, line of slope 1, and here also line of slope 2 or minus. All right, so this is the affine plane. And so, okay, yeah, you can see it has P squared points and P squared plus P lines. And now what we're going to do is make this thing quantum in the most obvious possible way. Which is as follows. We will just make uniform superpositions of all the points on each line. Okay, so it will be similar to what we had here, these sets, but we are, throwing away these points at infinity, and we're throwing away also this line at infinity. And so everything else that's left that describes this affine plane, and we're gonna make quantum states. And these states will be as follows. I will call them L because it's the line basically of those points. We'll have these two parameters, the slope and the shift. And it's just going to be a uniform superposition of everything that's on that line. So here's going to be X in a finite field. And in the first register, we just put X. And in the second register, we put X. All right, so we'll have these lines. And then we have also, we have to specially take care of the vertical lines because they have infinite slope. So these will be called, so this is just like here, this set of these points. The infinite lines will look like this, and in some over y because we're going vertically. And we start, so we shift it horizontally by 0, 1, or 2, and then we go up. So in the second register, we just put y. All right, so and so we'll have p square of these lines.
A quick question. Can I ask a quick question?
Yeah.
Are you restricting to prime powers now?
Yeah. So for this talk, I will talk about when the dimension is a prime, but the same idea also works for prime powers.
Okay, but nothing besides prime powers.
Yeah, so that's going to be in the open questions section.
Okay.
Yeah. All right.
So is there a reason that we should understand why you throw away the points at infinity?
Yeah. So the reason will become very clear. What we will want is that so what Harry and I came up is this map that we call doubling down, and because of this doubling property, we want to have two registers. So we want the total dimension to be a product. And basically, p squared plus p plus 1 is not a product, but p squared, for example, is a product. Okay? And so that's kind of why we throw it away. But yeah, I think maybe I'll just carry on, and then it will become clear why it is like it is. All right. So now what's special about this affine plane is just like in this projective plane, if you take any two lines, then, well, they either are parallel, like these, and then they don't have any point in common, or they intersect in exactly one. And so this, you can capture this by looking at inner products of these vectors. And so what inner products are, is if you take arbitrary two vectors, LA, LB, so what you get is as follows. So if A is equal to A prime, so if they are at the same slope, then they will be the same if they have the same shift, and otherwise they will have no points in common, and their product will be 0. And otherwise they will have exactly one point in common, so the inner product is 1 over p. So these are the inner products of these line states for the affine plane. All right, so now what's nice about this is that it reminds us some other structure it comes up in quantum information. So let me explain what this other structure is. And it has very similar, so it's a collection of vectors that have very similar inner products. So these are called mutually unbiased bases. So let me write down the definition. Okay, so what is a mutually unbiased set of bases? I'll just abbreviate them by MUB. So it's a collection of vectors. I will label them by two parameters. They are, in general, let's say, in dimension B. And so these parameters A and B, they will take, so A will take B plus 1 values, and B will take B values. And their inner products are as follows. By AB, by A prime, B prime, is something that looks very similar to what we had for these line states. So this will be B prime if A is equal to A prime. And otherwise, it's going to be 1 over. So we're going to put absolute value because these are general complex vectors. So this could be a complex number. But if you take absolute value, we get 1 over square root of B otherwise. Okay. And sort of intuitively, you can think about these as basically if you fix A, so the A determines a basis and B determines a vector within the basis. So you can think of this as basically having, if you fix A, there are D plus 1 possible values for A. D plus 1 for the parameter A, and for B there are D values, and so basically A tells you which orthonormal base you're talking about, and B tells you which vector inside a particular base. Okay. So these are the orthonormality relations. And now, is there any question about the definition of these mutually unbiased bases? All right, so maybe let me give a quick example in case you haven't seen these things. Okay, so the example is, for example, when D equals 2, then what we can do is we can take the following bases. You can just take 0, 1, plus minus, and then plus I and minus I. And pictorially, you can think of this as, if you're familiar with the block sphere, these are just the eigenvectors of the Pauli matrices. So if you depict these vectors in block sphere, they look as follows. You have 0 here, you have 1 here, pointing in a vertical direction up and down. Then along the x-axis, you'll have the plus and minus. And then along the y-axis, you'll have these plus I and minus. And so the reason, okay, so you can easily check that these vectors have the right inner products, like 1 over square root of 2. But sort of, I think what's important, what's kind of maybe also for intuition and also later for the second half of the talk, is if you take the inner product between two vectors that are the two cubic states, and if you square this, it's going to be the same as, so these live in C squared. And you can also take the inner product between the corresponding block vectors, R1, R2. So these live in R3. And so there's a relationship like this. And there's some special values that appear that are important in our discussion. So basically, let's say this is either 1, 0, or half. So if this is 1, then these two vectors are the same. And also here, it's going to, if you just do the calculation and compute what it means for this, it means also this have to be the same. Now, if the quantum states are orthogonal, if you do the calculation, here you're going to get -1, which means that in block sphere orthogonal, the states that are otherwise orthogonal, they point actually, they are antipodal, they point in opposite directions. And then finally, this 1 square, which is, this is mutually unbiased conditioning. Square it. So what does this say here? It says the inner product has to be 0, and you can see indeed these x, y, and z axes, they are perpendicular. That's why these vectors indeed make a set of mutually unbiased. And another special value that's going to be important later is if you look at the value 1/3, it's going to translate to -1/3. And so this is the angle of if you take a regular tetrahedron in 3 dimensions, and you take the angle between any two vectors in the tetrahedron, and you take inner product, you're going to get -1/3, and it translates over in a complex world to the 1/3. So these are some special values that are interesting. All right, so oh wow, I really have to move on. All right, so what we're going to do now is I'm going to explain how we can relate. So you see this relationship looks exactly like this, except you need to do some little bit of massaging. And so, okay, what's the difference? So there are two differences. One difference is that these vectors live in d dimensions, but these vectors, well, okay, so maybe let me not call it e anymore, let me call this e. We are restricting to the case when we have a prime. So then these live in p dimensions, but those lines, they live in p square dimensions. So that's one problem. And the other problem is that they have inner product 1 over p, but these guys have 1 over square root of p. So basically, we are off both in inner product and also in dimension. And at first, it looks hopeless. It's not clear if there's any relationship or if we can massage one vector into the others. But it turns out we can. And in fact, there's a unitary transformation. But we need to kind of we need to be a little bit more clever. And what we're going to do is we're going to double. Basically, we just want to, instead of getting one vector, we're going to get 2 of them. Okay, so basically what we want to do is, so this is this doubling down idea. So we are going down in dimension, and we are doubling the state, and we are also going down in the inner product. That's why we call it double down, and also in honor of the game that inspired this idea. Okay, so basically we have these vectors L and B, and we want to somehow so we want to find a unitary that has the property that it produces 2 of these mutually unbiased bases. Okay. And okay, so this was just a wild guess. We were brainstorming this hurry and we're saying, well, maybe this will fix it. This has the right dimension. And now if you take the inner product between these guys, they, because you have 2 of them, the inner product will square, so everything seems fine. But there's a slight issue, and it turns out this is not possible. But if you do this, then it is possible. So basically, we take complex conjugate of 1. And also intuitively, the reason we might want to do this is because in these mutually unbiased bases, since we take the absolute value of the inner product, it doesn't matter what the global phase is. And now if you do this, then the global phase also cancels out. So if you perturb these vectors by changing global phase, no, it doesn't matter. Now the question is, can we cook up a map that just maps these line vectors from this affine plane, the mutually unbiased basis vectors? Okay. Is there any question about what we're trying to do? All right. So no question. So let me just draw the circuit for this. It's going to be as follows. So we feed in one of these line states, and what we're going to do is, so there's a good reason why we're doing this. Let me just first draw the circuit and then I'll explain. And so what comes out here will be these 2 guys. Okay, and now, so what are these guys? So the F is just going to be a Fourier transform of the finite field, and in this case, it's going to be just size P. Use the same variables, Y, Z. So this is the P discrete of unity, the power of YZ, YZ. And now, what's going to be this mysterious operation P? It will just have the following definition. If you plug in X and Y, then what comes out is X plus Y over 2, and what comes out here is X minus Y over 2 for every possible choice of X, Y that is in a finite field. So, okay, so why are we doing exactly this? So one thing is this following. In the definition of these L states, we have one sum because the sum goes over the points on the line. But here we have tensor product of 2 things, and this is a superposition of something, and this is a superposition of something. So there are 2 sums here. So we thought, well, let's just do Fourier transform. That's going to introduce another sum. That was our way of thinking. And the second thing, why we do this, so this you can see is just a permutation. It permutes the standard basis vector because given these 2 values, you can just add them, you get X, and if you subtract them, you get Y. So it's reversible, it's permutation. And this was well, since we knew what these states look like, we managed to guess this. But this was, it was not so obvious that you have to do this. All right, so now let me quickly show you what happens if you do the circuit, and it's really easy to do the calculation. Yeah, so maybe I'll just erase here. And what is actually important is we don't, if we imagine you cook up a unitary that maps these line states to any product state, any state tensor with itself, then by definition, if you take the inner products of these guys, they will have the right inner products as in the mutual unbiased basis. So basically, you don't have to think of these vectors necessarily as specific vectors from UIB. All we want to do is we want to disentangle these line states. So if you look at these line states, you see they are actually all maximally entangled because the line sort of, it has, it's like a permutation, unless it's horizontal or unless it's completely vertical. If it has some kind of non-trivial slope, then it has all possible values of x and also all possible values of y. Basically, these states are all maximally entangled. And what we want to do is we want to cook up a unitary that simultaneously disentangles them into these products. And then if we manage to do that, we know that we're going to get the right inner products because we're just doubling down. So the inner products are just going to be, we're going to get square root of the inner products of these. Okay. All right. So let me show you that this indeed works. Okay. So all I want to see is that they get this. Okay. So if we start with this L and B. So first we apply we get transform on the second register. So what we're going to get is 1 over P. We're going to get two sums over x and y, omega P y a x plus b, and then x y. So basically what we have here in the register, this ax plus b just goes into the case. And now we apply this funky operation P. So all it does, it just replaces in the last register these x and y. It replaces by x plus y divided by 2 and x minus y divided by 2. So this was this T operation that is just a classical permutation of the standard basis. Okay, so now we have to do just a substitution of variables. So I will say that I will just call this A, I will call this L. Okay, so then what we get is 1 over P. The sum is over K and L. And so now you can, from K and L, you can easily solve back for X. So X is just going to be K plus L. And Y is going to be K minus L. So, okay, so what we get is, so Y is K minus L. Then A times K plus L plus B. And then in the register, we just have K. L. All right, and so here now is the magic step. So what we want to do is we want to disentangle these states. So we have K in one register, we have L in the other register. So we want to take this space and we want to split it as a sum of two things. One that depends only on K and the other one that depends only on L. Then we can put the K ones here and the L ones there. That's what we want to do, because then we end up disentangling this. Okay. So now, okay, so let's just see what this is. So if we open this up, we have A times K squared minus L squared, and then we have B K minus L. And we are extremely lucky, and this is why we chose this this T map exactly like this, because we wanted this to happen. We wanted to have it be able to separate the K's and L. So basically, what we can do now is just write A K squared plus B K, and then minus A L squared plus B L. Okay. So here we have only K's and here we have only L's. Right. So now it means that this state that we have here, actually you can write it as follows: 1 over square root of P, sum over K, also K is in a finite field. And then omega to that power, A K squared plus B K, and then K in the register here. And then in the second register, we just have a complex conjugate because we have a minus sign here. So we have 1 over square root of p, sum over L, omega to the power a L squared plus b L. And a big complex conjugate for the whole thing. Okay? And now this is just a state. We call this state psi AB. And this is just going to be the complex conjugate. Voila. And because we managed to disentangle, we know that we get the right inner products, and we know that these states, whatever they are, they have the inner products that we need in this mutually unbiased space. Okay? Just because they are the same. Is there any question about this? See how much time? Oh, wow, how much time?
Yeah, Marius, I have a question.
Yeah.
So vaguely remember a construction of Klappenecker, I believe, and co-authors where they used properties of Gauss sums.
Yeah.
Kinds of vectors
Exactly.
that involve these quadratic phases. So do you include all of their constructions?
Yeah. So okay. So this construction, so it produces exact. So there's a paper by Ivanovich from '81. So this is exactly what is in his paper, and that then Wouters and Fields later generalized this to finite fields that are prime powers. And it's basically the same, but you just have to do this over the bigger field, and then you have to do a trace of the field. So basically you get something like this. And indeed, if you want to check that these by construction, because the gates we did were unitary, and these guys had the right inner products, we know that these guys will have the right inner products. You can also say, well, let's explicitly check that. And if you would explicitly want to check this, you would say, well, okay, so we want to say, let's say, for example, the inner product between psi 0, 0 and psi AB. And what this is, so it's going to be 1 over p, and then a sum over, let's say, some k, and then omega a k squared plus b k. And, you know, indeed, it turns out this is equal to 1 over square root of p, and this is indeed called the Gauss sum. So basically, Gauss showed that this identity holds, and it's really not obvious that it should hold. Imagine if you remove this, if you multiply everything by p, then what you get is you get the following thing, you get square root of p. And so it's like you summing a bunch of roots of unities. You are kind of walking a complex plane, taking unit steps, and you end up at exactly this square root of p. Well, it's not obvious this should be the case, but yeah, indeed, Gauss, this is called Gauss sum, and Gauss showed that this is the case, but it also follows sort of implicitly from our construction. All right, so yeah, unfortunately, I was much slower than I was hoping. So maybe let me say quickly what happens, what else we can do with this, because affine plane is not the only thing that we can double down. And in fact, what we can also double down is the dual of the affine plane. So what we did here was we removed this line at infinity and all the corresponding points, but we can do the other way around. Instead of removing one line, we could remove 1 point from the plane. So we call this the punctured projective plane because we just made a hole by removing 1 point. But okay, so I'm not sure if I said this earlier, but this projective plane actually is self-dual. So you see this matrix, it's a square matrix, and in fact, if you arrange these lines and points in the right order, you can make this matrix symmetric, meaning that there is a bijection between the points and lines. So you can sort of, if I make any statement about points, like let's say, any 2 points that terminate a line, the same is also true about the other way around if I exchange the words point and line. Because this matrix is symmetric, I can just exchange the points and line. And so, and basically, if we instead remove a point, we end up with incident structure that's just described by the transposer. So instead of treating the columns as lines, we would treat the rows as lines, and we would treat the columns as points. And now, okay, so I will not have time to explain it in detail, but the dual structures of this punctured projective plane, it has the following. If you cook up these line states, I will call these line states, I will call them by P because they are sort of, they are point states, they are kind of dual. So if you cook up these point states, they are just, instead of, okay, maybe let me draw a picture. So here, what we were doing were we were taking uniform superposition. We're basically taking the columns, and we can instead just take uniform superposition of these guys. Okay, so these are the point states, and these are the ones. And these point states, if you compute inner product between them, they have inner product that looks like this. So it is 1 if A is A prime and B is B prime, and 1 over B plus 1 as well. And so these inner products, so basically if these both indices are equal, well, then inner product is 1, these are unit vectors. And if they are not equal, if there's any other combination, then you always get exactly this. And this is basically because any 2 points, yeah, so it's because any 2 points determine a unit line because of that. And so what we did then is ask, well, can we double down on this as well? And so here there's a little bit, it's a bit more difficult because the number of dimensions here is p squared plus p. So we're not going to get the unitary matrix, but we're going to get an isometry. But indeed, what you can do is you can cook up an isometry that's going to look like this, and you're going to get some vectors, some double down vectors phi. And again, I put complex conjugate here. And now, because we're doubling down, well, these are going to have dimension d each. So this will technically have dimension d squared plus d, but this is going to be isometry, so it's going to be fine. And then the inner products are just going to basically pick up a square root. And a collection of such vectors is called symmetric informationally complete POVM. And the question is, you know, how do you describe this isometry V here? So here, in case of uniform unbiased bases, we just do Fourier transform on one register, and this funny adding and subtracting operation afterwards. And for this, we worked out also an explicit formula how to do this in case when these guys exist. But I think because of the time constraints, I will not have time to explain. But maybe let me just say one.
Marius, you can take. We started late. You can take another 7 minutes, I guess.
Okay. All right. So okay. So then I can tell a little bit about how to construct this V. Of course, just to, you know, those who maybe know this problem and they might get excited, oh, we're going to solve a big problem. We're not going to solve the big problem. So we're going to basically, we're going to use information that we need to construct these POVMs in the first place. And we will plug those magic numbers, we'll plug them in and make this isometry. So we're not going to solve, so constructing these POVMs is a major open problem. And also understanding the solution unbiased bases, in particular in dimensions that are not prime powers, is also a major open problem. But you know, we are just going to be dancing around this problem and looking at it from different angles. We're not going to solve this, and maybe, you know, maybe these ideas could be used to make some progress. But I'm not claiming that. I'm just saying that we have a kind of a new perspective. This idea of doubling down. All right. So let me briefly say about these POVMs. So all their constructions are interestingly of the form that these vectors phi can be obtained by. Actually, you don't need to find, so in total there are d square vectors because these have d values close. You don't need to find all of them. And what suffices is just to find a single vector, and then you can get the other ones by applying these generalizations of power. So basically there'll be just one vector. This is called a fiducial vector. And you can generate all the other ones by applying x and z. And x and z are in general just going to be these generalized Paulis. So basically, x is just adding 1 to the standard base vector modulo d. It's like a cyclically shifting around. And this z will just pick up a phase of omega. Let's say we are in dimension d. It just picks up a phase x. Yeah. Okay. So, and you know, basically, it turns out that basically all known constructions are of this form, and in fact, it has been shown that in prime dimensions, this is the only way to do it. You just need to find one vector, and then you apply this x and z to generate all. Okay. And so now what we're going to do is, so let me explain how we construct this isometry V. So basically, this is a point at which I got coronavirus, and we were thinking about this, and I couldn't really do anything. But basically, once I recovered, then I started running some numerics to try to make a guess how on earth are we going to describe this isometry V. And I was just running numerics and staring at the output and running it again and staring again. And after some time, I came up with the following idea that what we should do is, so we're going to use the following ansatz. So we're going to say that if we act on on a product vector. So remember, what we want to do is we want to act on these sort of maximally entangled states. They're kind of spread all over the place. But let's say if we act on product states, we just want to know like what is like a specific column of this isometry V. And if the column is labeled by X and Y, then I made the following guess that it should be the following. Minus X divided by 2 minus X divided by 2 X conjugate, and then sum over K, some magic numbers. Okay, so what this is saying is that each column of this isometry V should be some kind of entangled state, Kk here, who has Schmidt coefficients like this. And the basis in which the Schmidt decomposition appears is given by this, where these M are just the mutual unbiased state basis. So basically M A would be just the sum over V, and we put these MUB vectors as column vectors. So these M's are just the basis A, and you stack all these vectors as column vectors. So this is some unitary. So this is unitary basis change, and we need to take this unitary in this way, and we have some funny stuff going on, some funny coefficients. And then similarly, there's a point at infinity because we're looking at this dual structure, so we have some infinity still there, and this will have some formula that looks very similar. And it just has some other coefficients that we need. So basically, the question is, how can we find these? Coefficients? So basically, I was running numerics, and I could see I could do this, and I could see always this isometry had this particular form. All I had to do is find these magic coefficients. And okay, so it turns out that these coefficients are very hard to find, and basically they are as hard to find as finding this fiducial vector itself. Basically, if something gives me this fiducial vector, what I can do is I can reconstruct these coefficients, and I will get this big isometry, and it's going to double down. But I cannot just guess these coefficients from what we were doing. Basically, I can relate these coefficients to the coefficients of this fiducial vector, and so I think I'm not going to write it out in all glorious detail. Well, I guess I can just write it out. So anyway, so it's not so bad. So basically, so I guess our result concerning these SIC POVMs is as follows. We have a formula for this isometry V, and since stacks in two systems has two registers here and two registers there, here's like some S and P. These are basically all possible entries of this isometry. And we have some explicit formula. Maybe I'm not going to write it out, but it's in terms of phi, well, it's called phi s, which are just the s component of this fiducial vector. Okay. So basically, the way you can think about it is that if somebody gives us this fiducial vector, all these numbers that are needed to construct this SIC POVM like this. What we can do, we can just plug these numbers in our magic formula, and we're going to get a big unitary that has the property that maps the dual affine plane to the SIC POVM vectors in this map. Okay? So it kind of, it basically puts a new angle on this SIC POVM problem, and also it sort of shows that they are very similar to these fusion and bias bases. And in fact, in some sense, they are dual because in one case, we were doubling down on the columns of this incidence matrix, and on the other case, we were doubling down on the rows. And in fact, so this is something I don't know. This, I guess, this is something I find curious, but I don't know what it means. If we call that matrix A, then we can double down both ways simultaneously. So we can ask, well, what is UAB transpose, where this is the MUIB matrix, and this is the SIC POVM matrix. Basically, if you multiply these two, then you get the MUIBs. If you multiply instead these two, then you get the SIC POVMs, and you can kind of multiply them all. You can double down both on the lines and points simultaneously, and you get some crazy matrix. And yeah, I just wonder what that matrix means. So yeah, so this is basically it. And we have lots of questions because, you know, of course, you know, the question is, does this say anything about the existence of these objects? And so I think that there is one problem, is that basically all our constructions use finite fields. So this mutual unbiased based construction, you know, it uses finite fields. We need to construct these lines and so on. And similarly here also we need finite fields. And so basically we cannot do anything if the dimension is not a prime power. So it's not clear how to do any of these things. And it's even less unclear how to try to even do these things in a dimension independent way. So let's say you wanted to show, for example, that mutually unbiased bases don't exist. Let's say in 6 dimensions, 6 is not a prime power. So what you could do is you could say, well, let's take some, you know, let's presume there is some mutually unbiased base in 6 dimensions. Let's try to go the other way around. Let's try to, you know, instead of doubling down, let's try to double it up to get some affine plane. And we know that there's no affine plane in 6 dimensions, you know, then we are golden. But the problem is that these maps that we cook up, they go in the, first of all, they go in the other direction. They go from they start with this discrete structure, and then they end up with these lumps of POVMs, and they explicitly use finite field. So if the dimension is arbitrary, it's not even clear, like, you know, we cannot just write this map down because the finite field doesn't exist. We cannot just plug in some arbitrary numbers there. It's just not going to work. And so it's basically not clear to me what does this say, in dimensions that are not prime powers. But I think there are still interesting questions one can ask. For example, what one can ask is, for example, these SIC POVMs, in some dimensions, they are not unique. There are several you know, different fiducial vectors that genuinely different that still work. And what you can do is you can, if you double them up into this world of these kind of lines, then when you double them up, you will get vectors that look like this. And the Gram matrix of these vectors is just going to be the same as the Gram matrix of this line state. And in fact, it's not going to depend on the SIC POVM anymore, because it's just going to be this fixed Gram matrix of these lines. And so it means that you can actually double up any SIC POVM, and then you can do a big unitary that maps one to another, and then you can double it down again and get the other. So basically, kind of, in principle, you can construct unitary maps that map inequivalent SIC POVMs to each other by sort of doubling them up and then doubling them down. Yeah. I think that's kind of interesting. It would be interesting to explicitly write out what this map looks like in terms of the two fiducial vectors of these SIC POVMs. And I think in terms of MUIBs, one can also ask some more questions. Like, I don't fully understand if they are equivalent or not in given dimension, but if they are not equivalent, then also one can sort of double them up and down and still get a map. Yeah, so these are the main questions that we have. But if anybody has any other interesting ideas where this could go, and of course also the question is, could this have some application like these maps UvA? They are, you know, okay, we just construct them in this sort of mathematical. We just get interested because there's some nice math, but could they be used because they're unitary? Could they be used in some either quantum algorithm or some kind of quantum protocol, which is some interesting task? That's also an open question.